Hey everybody, and welcome back. This is the first lesson of Unit 6. All right, so we are going to be diving now into exponential functions, and we're going to try and get to logarithmic ones as well. They kind of go hand in hand. A logarithmic function is the inverse of an exponential function. But we'll really focus on the exponential side first, and then we'll get into logarithms if possible. And that's going to bring us to the end of our Algebra 2 experience. So thank you so much for being here, and let's really dig into this last unit. All right, so goals for today, we're going to look at the parent function, and I put functions in there because you're going to see in a second, there is a little bit of a caveat to that for exponential functions. We're going to look at their characteristics, we're going to look at what growth and decay means, and then we're going to look at transformation, so your standard ones for anytime we see a new function. Now, there is an additional kind of function I want to throw in here, and that is an exponential function with a base of e. And that is not a typo, so e is like pi. It is an irrational value that has a special meaning in mathematics. So E is what we call the natural number or Euler's number. Essential questions. How can we tell if an exponential function is a growth or decay function? And then how do we change the equation using transformation? So basically, how do you manipulate the function? Where's the a, b, h, k? What do they do? And that sort of thing. All right, in the last lesson, which was the end of Unit 5, we talked about solving radical equations. We checked for extraneous solutions, and then we solved some word problems as well. So very much to do with solving. All right, so exponential functions. We've got a parent function of b to the power of x. Now, that means there's two variables going on here, and that's kind of important because really this b value can be anything, and then it's still a parent function. So that's the hard part. Some characteristics that have to be there, b has to be positive. So b is greater than 0. That's pretty much it. Like this number has to be greater than 0. If it's negative, we consider it to have a negative a value and then times a positive b. So the negative will always be absorbed by this first number instead. So when we look at these, there's two different types of exponential functions. There's exponential growth and exponential decay. Exponential growth is as you move an increasing x value, so from left to right, the value of the y component is increasing. So it's increasing, towards infinity. So not towards an asymptote, but towards positive infinity or negative infinity. You could have something that looks like this as well, and that would be an exponential growth, but in a downward fashion as opposed to upward. So this function over here is f of x is equal to 2 to the power of x. So we have a base value of 2. So the parent function in this case is 2 to the power of x. Exponential decay, on the other hand, as you move from left to right, or as x increases, the value of y approaches an asymptote. So it exponentially gets closer and closer to that asymptote. So it's, in our case here, it's going towards 0. So this function is f of x is equal to a half to the power of x. So as you take a step to the right on x, the value of y gets cut in half each time. So we can see like -2, 4, -1, 2, 0, 1, a half, a quarter, an eighth, like you get the idea. So we want to be able to identify, okay, when is it growth, when is it decay? It's growth when the b value is anything greater than 1. So it can't be equal to 1, it's just greater than 1. It's a decay function if the b value is between 0 and 1. So notice that if b is equal to 1, it's not an exponential function anymore because 1 to the power of anything is just 1. So you would just get a flat line going across at y equals 1. So it just cannot be equal to 1, but it also has to be positive. So anything greater than 0 but not equal to 1, that's your values for b to get an exponential function. All right, so transformations. We've got that parent function b to the power of x. We're only going to talk about a values, and then we've got h and k as well. So we're not going to, the b in this case is not a horizontal stretch or compression. So we're going to just leave it for a at the moment, and we're going to keep b in there as that parent function. So that's your base value. So parent function is b to the power of x. A is still that reflection over the x-axis, and then vertical stretch or compression. B is what we call the growth factor or decay factor, so that's that parent function part. H is the horizontal translation, so right, left, and K is up, down. One other thing to note, we have an asymptote, and the asymptote is going to be equal to the k value. So it's a horizontal asymptote. So the value that, if it's decaying, that's decaying towards. If it's growing away from. So if we're given this function, g of x equals -2 times 3 to the power of x minus 3 minus 8, we would say, all right, the -2, so there's a reflection over x-axis. There's a vertical stretch by a factor of 2. The base value is 3, so we would just say, or the growth factor, so this is an exponential growth. So growth factor is 3. That means for every step we take, it's tripling in value. X minus h, so that means x minus h is equal to -3, which means h is equal to 3. So we've got a translation right 3 units. And then our k value is -8, so we got a translation down 8 units. Wasn't asked for this, but horizontal asymptote would be at y equals -8. So it's just the same as the k value. So if I were graphing this, so we'll say this is my x-axis, horizontal asymptote at -8. And then it's moved 3 units to the right. All right, so it would look something like this. So it's still growing away from the asymptote because it's a growth factor by a factor of 3. So every step we take, so this would be -9, and then the next step would be at, oh gosh, -12, and then it would, keep tripling away from there. All right, identify the transformations on the given function. So you've got 2 examples here. What are the transformations? You guys know how to do this, and then come back, check your work, and see how you did. All right, so we've got an a value of 3, so this is a vertical stretch. So we can have a vertical stretch of 3, but it can still be a decay function. So it's got a b value of 1/2, so the decay factor is equal to 1/2. So every time we move a step to the right, it's getting half of its original value. There's no h value, so you could just put h as 0, but there's no translation. But we do have a translation down. All right, so now this one we've got a reflection. We have a decay factor again, or sorry, no, we have a vertical compression. Of 1/4. We've got a growth factor of 5. And we're moving left 2 units. And then there's no translation up or down. All right, so we got 2 functions, and we want to check out domain, range, and behavior, which is what we typically do for most of our functions anyway. So when we think about what these look like, we saw the graphs earlier. So this one starts at 0 and then grows up. This one coming down from infinity and approaching 0. Both pass through the point 0, 1. That's kind of the key. All right, so in terms of domain, range, and behavior. Domain, like most of our functions, the domain is from negative infinity to positive infinity. It goes forever in both directions. So even though this is sharply increasing upwards, there's never a vertical asymptote. It's going to continue to have more x values as we move to the right and a y value to go with it. Range, now this is one where you do have to be a little bit more careful. The horizontal asymptote is going to be the lowest point on your range. If it's growing upwards, it's going to be the highest point if it's growing downwards. So our range in this case is 0 to positive infinity, and notice that the 0 is not included because it is an asymptote. It does not ever actually reach that value. And then end behavior, as x goes towards positive infinity, y goes towards positive infinity. As x goes towards negative infinity, y approaches 0. So the horizontal asymptote. So it's not always going to be 0, it's going to be whatever the horizontal asymptote is. For the exponential decay function, almost the exact same thing here. So minus infinity to infinity, range, we got 0 to positive infinity. So even though it's coming from the positive infinity side, it's coming down approaching 0. End behavior, as x approaches positive infinity, y approaches 0. So it's reversed from what we saw in the last one. Negative infinity, y approaches positive infinity. So as we move to the left, it goes up towards that positive infinity. That's it. I mean, you guys know how to do this. You should be very comfortable identifying things like domain, range, and end behavior. All right, so this is the one that'll probably cause the most challenge because it's just a little bit new. So when we are writing the equation of exponential functions, a couple of things, you have to be given the parent function, so what the b value is, the growth or decay factor. You need to know what that is to be able to answer this question. Otherwise, there's multiple answers to the same question, because it could be a exponential growth from left to right. It could be an exponential decay, but with a reflection as well. Like you don't know. So they're going to give you that information. They're also going to give you the first reference point. So this one is the first reference point. So what you've got here is your h value is your x coordinate, and then a plus k makes up that y coordinate. We're going to be able to identify k because it's our asymptote. So looking at the value that it approaches, that's where we get our k value from. So that means we're allowed to solve for a. So it's different to how we solve for all of our other equations so far. So we would say b is equal to 2. So for that reference point, minus 1, 5.5, h is equal to minus 1, and then a plus k is equal to 5.5, and we know k is 4, so a plus 4 equals 5.5, which means a equals 1.5. So then this function would be g of x equals 1.5 times 2 to the power of x, and we've got h is minus 1, so if it's x minus h, this is x plus 1. And then we've got k is plus 4. So it's a times b, x minus h plus k, don't forget. So we're solving for a still, that nothing's changed about that, it's just that we have to solve for it in a different way. So make sure you've got this little formula tucked away somewhere. So h is the x value, a plus k is the y value for the reference point that you're given. Sometimes you'll be asked to verify your answer. So that means you would take your equation that you just found and you would plug that into using another point. So in this case, like if we were given the point 110, we'd have to check our answer. And I just realized I wrote k in my equation. That should be a 4. So if I were going to check my work now, I would use the point 110. So 10 is equal to 1.5 times 2 to the power of 1 plus 1 plus 4. So 10 equals 2 to the power of 2 is 4. 4 times 1.5 is 6. 6 plus 4 is 10. So I'd be like, yes, this function works. So if I take another point on it, I can verify that my function is correct because it does, in fact, fit the function. So just be aware of that. If you're asked to check your work, that's what they're looking for. All right, your turn. Can you please write the equation of the exponential function? You're given the b value is a half, so this is a decay function. And notice that it's coming from negative infinity up to 5, so you're expecting a negative a value. But I won't say any more. Try it out, pause the video, come back, and then check your work. All right, so as I said, there is an asymptote at k equals 5. So k is equal to 5. We've got that first point at 2, 2. This means h is equal to 2. A plus k is equal to 2. And k is 5. So a plus 5 is equal to 2, which means a is equal to minus 3. And we said we were expecting a negative a value, so that's perfectly fine. So g of x is equal to minus 3 times a half. A lot of times with the fractions, we'll put the parenthesis around it just to make sure we know that the exponents are being applied to it and that it's an exponent, not another fraction. So we got x, I said h was 2, so x minus 2, and then k is 5, so plus 5. All right, being asked to check our work, it looks like 1 minus 1 is another point, so let's see if that one works. So that'll be minus 1 is equal to minus 3 times a half to the power of 1 minus 2, which is minus 1, and then plus 5. Okay, so that'd be minus 1. A half to the power of minus 1 is going to be 1 to the power of minus 1 and 2 to the power of minus 1, which is just a positive 2. So it's going to be minus 3 times 2 plus 5, so minus 6 plus 5, which is minus 1, and it's equal to minus 1. So yes, we have verified our answer. It is correct. All right, last thing I want to tell you about. Now, we're only talking about it today. We're not going to do any problems related to it. It's more of an introduction because we're going to need it in future lessons. But let's just kind of think about what it means. So the value e, it's called the natural number. Now, it's not the set of natural numbers. That's a different thing. This is the natural number, also known as Euler's number, after the mathematician who basically derived it. So what it is, or how we get it, it's 1 plus 1 over x to the power of x. So the higher you increase the value of x, the closer you get to this value, 2.71828. So we usually approximate it as 2.718, kind of like the way we do with pi, like 3.14. E, we do 2.718. It's called the natural number because it does appear a lot in nature and in the natural order of things that we see in life. It's a number that comes back up over and over and over again, like pi does. Like pi is just the circumference of a circle over its diameter. It's the same thing kind of here. Like we see this number popping up a lot in nature, and it's definitely got some mathematical purpose too. Particularly in this unit, we're going to be talking about it with population growths and also with compound interest. So you may see it in there as your base value, just knowing that it is not a variable. It is a symbol that is a placeholder for the value 2.718. It's an irrational number, by the way. So like pi, it cannot be expressed as a fraction, nor does it have any endpoint or repetition. So that's why we use the letter e to represent the full value of e. You can find it in your calculators. If you're working off a TI calculator, it's located above the division sign. So you'll notice the little lowercase e. You can also see it in some of our math options or above the ln option. All right, essential questions for today. How can we tell if an exponential function is a growth or decay? You're looking at the b value. So if b is between 0 and 1, it is an exponential decay function. So it's getting closer to the asymptote as you step closer to positive infinity for x. And then it's an exponential growth function if the b value is greater than 1. So in both cases, it cannot be equal to 1, because at that point you just have a linear function. How do we change the equation of an exponential function to transform it? The a value, so that is going to be your vertical stretch or compression, or you can make it into a reflection if you make it negative. The h value, move it right left. the k value up, down. If you change the b value, you are changing the growth or decay factor. So that really doesn't transform it anymore. That's creating a completely different exponential function. After this lesson, you've got the Module 1 folder. So just complete that, graphing and interpreting exponential functions. So independent practice discussion question. I'll see you soon.